So today we're starting section 5.1, which is linear models, initial value problems. These are physics applications. This is split into three different sections, or three different parts, rather. We're doing 5.1.1, which is free undamped motion. So we're going to do undamped motion, we'll do damped motion, and then we'll do driven motion. I think this stuff is review from physics, I believe. Okay, here's what we're looking at. We have some spring that has a mass attached to it. When the mass is just hanging and not moving, we say that the mass is at equilibrium. We're looking at what happens when you pull the mass down or you push it up. The amount that you move the mass away from equilibrium is going to be x. So then what we could also do is we could push the mass up with a force. Again, this is x, the amount that it goes away from equilibrium. Okay. This involves two different laws with force. Hooke's law and Newton's second law. Okay. So Hooke's law has to do with the force of the spring on the mass. So this has to do with the spring. Okay. What Hooke's law tells us is that the force is proportional to what I'm going to call the stretch distance. Okay, and then we also said Newton's second law, which is the force due to gravity. So force, which we're also going to use weight sometimes in place of force, is equal to mg. M is the mass. If you remember, we use different mass units than you use in physics. The mass that we're going to use is in slugs. G is 32, bless you, feet per second squared. Okay, when we are at equilibrium, the force due to gravity is equal to the force of the spring on the mass. That should make sense, the mass isn't moving. So the force of the spring on the mass and the force due to gravity are equal. So at equilibrium, mg minus ks is going to be equal to 0. Okay, we're going to use that later. When the object is displaced, the net force is equal to ma. So if the object is displaced, there's still force due to gravity, there's still force due to that spring. So we have a net force then. That net force is going to be the force due to gravity, which doesn't change. So that's force due to gravity. And then we still have the force of the spring that is on the mass. So that is negative k. And then it's the stretch distance. Now, the stretch to get to equilibrium is s. Any amount that we move from equilibrium is x. That is the net force. Okay, so then on this side we get negative ks minus kx plus mg. Those two we said is equal to 0. So So what we get is MA is equal to negative KX. Now, we're in differential equations, so our objective is to write a differential equation and then solve it. We don't have any differentials in here yet, so we need one. Acceleration we're going to write as a derivative. It's the second derivative of position. So we get m, second derivative of position, plus kx is equal to 0. We generally like to write this in standard form, so we're going to divide by m. Now, we have solved this before in this chapter. This is homogeneous and it's linear. How did we solve a homogeneous linear differential equation? Last chapter, I mean. I can't understand you through all your mumbling. How did you solve a homogeneous linear differential equation, which is on the test you have tomorrow? Yes, what? Who said that? The aux equation or the characteristic equation? So you changed things to m, and then you factored, you did the quadratic formula? Right? Sound familiar? Yes. Okay, so this one would be m squared. Now it's not this m though, different m. M squared plus k over m equals 0. Do you see that you would end up moving that k over m over and taking the square root? Okay, which is not going to look super nice. So normally what we do just to make the calculations easier is we replace that with a new constant. So that's what we're going to do. The constant that we replace that with is omega squared, just to make our calculations easier. Okay, this leads us to our general solution. So the equation that you're going to be looking at is x double prime add omega squared x equals 0. So that's exactly what we have above. How many initial conditions are we going to need to solve? 2. Generally, you'll have x of 0 equals alpha, x prime of 0 equals beta. Okay, let's think about this. What does x of 0 represent in terms of our mass? Okay, what does x represent? The distance from equilibrium. So the distance from equilibrium at time equals 0 is alpha. So it's like your starting position. What is x prime? Velocity, the initial velocity. So at time 0, the initial velocity at which the mass is moving. Okay, so then we said you would look at your auxiliary equation, which in this case is m squared add omega squared equals 0. If we were to solve that, our m is equal to plus or minus omega. X of t then, omega I. That makes a big difference. Okay, what kind of functions then are we going to have in our solution? Trig. Okay, so we're going to have c1 cosine of omega t plus c2 sine of omega t. So that is your equation of motion. Few things that we need to know, and I believe in physics this is the same way. When you pull the mass down, we're considering x to be positive. When you push the mass up from equilibrium, we're considering x to be negative. Two other things you need to know before we do an example is the period of motion. If you're asked for the period of motion, that is 2 pi divided by omega. By period of motion, I mean how often the graph repeats within 2 pi, that is. Okay, frequency, that's equal to omega divided by 2 pi. What I mean by frequency is the number of complete cycles in 2 pi, 2 pi being our unit of time. Okay. Any questions so far? Okay, within this undamped motion, there's 2 expectations I have. The first expectation is that if I give you an equation, you can interpret what that means in real life. And then, given a real life scenario, you can solve for x. So we're going to do both of those. Here's our first example. Okay, so we're going to solve, and then we're going to say what this represents. 10 is your omega squared. So our solution then will be x of t is equal to c1 cosine of omega t, which in this case is root 10t, plus c2 sine of root 10t. We have 2 initial conditions. One of them is going to need the derivative, so I'm going to take the derivative of this before I start solving for c1 and c2. X prime of t will be negative root 10 c1 sine of root 10t plus root 10 c2 cosine of root 10t. First, I have x of 0 is equal to 5. So I get 0 is equal to c1, not 0, 5 is equal to c1 plus 0, so c1 equals 5. X prime of 0 is equal to 0. We get 0 is equal to 0 plus root 10 c2, in which case c2 equals 0. So our equation of motion then is 5 cosine of root 10t. If you are asked for the period, that's going to be 2 pi divided by omega. Frequency is the reciprocal of that. Okay, I also want us to describe what this represents. What does this x of 0 equals 5 mean?
Times 0, it's stretched 5, whatever.
Right, at time 0, the mass is 5 units in what direction?
Down.
Down. Okay. So the mass starts 5 units below equilibrium. Please make sure you somehow get that below part. So it's stretched down somehow. You tell me that it's below. Equilibrium with. What does that x prime of 0 equals 0 mean? With initial velocity. So with initial velocity 0, sometimes the way that'll be worded is that the object is released from rest. That's the same meaning. Okay, so then once it's let go, the object oscillates back and forth. According to x of t above. If we were to graph this, object starts 5 units above equilibrium, or below equilibrium rather. The period is 2 pi over 10. So that's when the graph will start repeating itself. If we graph cosine, something like that, and then it'll do the same thing again. So this will be 4 pi over, it's actually root 10. Okay. Questions before we keep going? Great. Okay. Here's our next example. A 2-pound weight stretches a spring 6 inches at t equals 0. The mass is released from a point 8 inches below equilibrium. With upward velocity 4/3 feet per second. We are finding x of t. Okay. So the general equation that we started with at the beginning of the notes looks like this. So we need to find m and we need to find k. Okay, this is one that we looked at, F equals mg. And I said sometimes instead of F, we're going to use W for weight. We have the weight here. So our weight of 2 is equal to the mass. G is 32. So our mass ends up being 1/16. That's a slug. We also looked at F equals K times S. Instead of F, we're going to use weight again. So we're going to use 2 again. Okay, for S, the weight stretches the spring 6 inches. That's going to be our S. But remember that that 32 is in feet per second squared. So we need to stay in terms of feet. 6 inches then is half a foot. So we get our K to be 4. Now we can go back to this equation. So we have 1/16 x double prime plus 4x equals 0. We multiply by 16, we get x double prime plus 64x equals 0. Good? If we use the auxiliary equation, we're going to get m is equal to plus or minus 8i. So our solution then is C1 cosine of 8t plus C2 sine of 8t. So next thing we're going to have to do is figure out our initial conditions. First thing is at t equals 0, the mass is released from a point 8 inches below equilibrium. Below equilibrium is positive, so we get x of 0 equals what? Two-thirds. Because remember, we want everything in terms of feet. Initial velocity is upward 4/3 feet per second, so that'll be negative 4/3. Because we're upwards. Okay. Can I trust that you guys can find C1 and C2? Do we need to go through it? Okay, great. Your solution then ends up being x of t is equal to 2/3 cosine of 8t minus 1/6 sine of 8t. Okay. Any questions before we keep going? You all have done this in physics, right? Okay. Does your answer normally look the way that ours does? No. How do you express your answer in physics? You never have an equation? It's with what? Constants? There's never an equation? No? Okay. Cool. Well, I thought you guys had done it within an equation before. This is not super helpful. I might ask for the amplitude, let's say. So the amplitude on example 1 was just 5. That's the highest point it hits. It goes between 5 and -5. This is very difficult to find the amplitude of. So this is not a very helpful form. There's another form that we're going to use that'll help us find the amplitude. So what we can do is we can take this equation and make it just sine or cosine. I believe in physics, generally everything is in terms of cosine. It's just a single function in terms of cosine. In differential equations, we're going to do sine. So your alternate form, x of t, is equal to a sine of the quantity omega t plus phi. A then is the amplitude. A is the square root c1 squared plus c2 squared. For phi, which is the phase angle, picture the triangle with c1 here and c2 here. Okay, now the question is, why are we allowed to do this? Why can we just take those two and combine it in this way? So we're going to talk about why we're allowed to do that. First thing we need to remember, sine of s add t is equal to sine of s cosine of t plus cosine of s times sine of t. So if we look at our x of t being that a sine of omega t plus phi, if we expand that out using the identity above, we're going to get a sine of omega t cosine of phi, add a cosine of omega t sine of phi, so this is a sine of omega t. Cosine of phi we can find up here. It'll be c2 divided by the hypotenuse, which would be the square root of c1 squared plus c2 squared, plus a cosine of omega t. Sine of phi, we can find that as well. this denominator we should notice is A. So this A will cancel the denominator, this A will cancel that denominator. So we end up getting C2 sine of omega t at C1 cosine of omega t, which is what we wanted. Okay, so let's return to example 2. We're going to put it in the alternate form. So we had 2/3 cosine of 8t minus 1/6 sine of 8t. For our A, it's going to be the square root of C1 squared, so 2/3 squared is 4/9 plus 1 over 36, which is root 17 over 6. To find phi, using this triangle where you're going to use tangent, so we get 2/3 divided by negative 1/6, which is negative 4. You end up getting phi to be negative 0.133 radians. Now, this is the one that's tricky. Remember that tangent is negative in 2 different quadrants, so you need to make sure that this is the tangent that you want. What quadrant will this be in? Negative 1.33 radians is in the second quadrant. This is definitely the fourth quadrant. Whew. Okay, if we go back to what we started with, numerator is sine, denominator is cosine. In which quadrant is sine positive and cosine negative? Second. So we want an angle that's in the second quadrant. I don't mean that to be a phi, I mean it to be a q. So we have something that's in the fourth quadrant, we want it in the second quadrant. So what do? Add pi to it. If we add 2 pi, we'll be back to the fourth quadrant. So then we get our phi to be about 1.81. Okay, so our alternate form then will be x of t is equal to root 17 over 6 sine of omega t add phi Okay, there's 2 things mainly that you'll be asked, bless you, with this. I could ask you the amplitude, which is root 17 over 6. So that's the furthest away that the mass is going to get from equilibrium in both directions. I could also ask you when the mass is at equilibrium. So that'll be when your distance away from equilibrium is 0. So when that sine of 8t plus 1.81 is equal to 0. When is sine equal to 0? Zero and pi, but remember we want all the times. So it's really at pi k, where k is an integer. So our t ends up being pi k minus 1.81 over 8. On your homework, you're going to be asked some other questions as well, like what is the first time the object passes through equilibrium going up or going down? So hopefully you can figure that out. Do we have any questions?